Today's speaker is Jacqueline van Gorkom from Columbia University. So just to give a little background on Jacqueline, she got her PhD at Gorkom in the Netherlands in 1980, I think. And then, it was so long ago. And then after that, she moved to the VLA right after it first opened to work as a staff scientist there. And then in 1988, she moved to Columbia, where she is now. So today she'll talk about gas and galaxy evolution from voids to clusters near and far. Let's welcome Jacqueline.
And the main point I want to make in this talk is that we are actually just about ready for a big revolution in radio astronomy. Right? So we have been using for years the VLA and Westernward, and this is now changing very rapidly. So the VLA has been upgraded, Atlantiva, NIRCAT, and SCAT are about to come online. And then they're hidden in the dark is a model of the SKA, which eventually will come to. So that's the future, and that is really, so I think we are very close to being able to do things that we've never been able to do, and in fact, on top, I try to convince you that we are already there. We are doing things that were impossible just a few years ago. So why are we talking about gas and galaxy evolution? So first of all, hydrogen is the most abundant element in the universe, and we know still very little about the evolution of it. We have Lyman alpha and Cloud alpha things, but we don't know anything about H1 emission beyond the redshift of about 0.08, which is really low. And I'm trying to convince you that just knowing the H1 content of galaxies is really not enough. It won't tell you much about galaxy evolution. And images can help you to clarify the mechanisms that actually are working on these galaxies, how they evolve. And so that all of that is just going to change in the next few years. So the major questions, of course, are how do galaxies grow in the local universe, and when and where do they stop growing, and how does this change with redshift? That's what we want to know. Okay, so I'll talk for 1 minute about simulations, because you all know a lot more about it than I do. But so there have been also in the last decade, there has been really a revolution in simulations of galaxy evolution, and so this is from the Millennium simulation, which is already quite old now. But what it shows is that in dark matter, this nice structure forms. It starts at high redshift, the universe is very, very flat. At z equals 0, the universe is mostly filled with voids, and voids are actually really, really interesting empty regions. So this is how the structure forms in dark matter, and I suppose you do understand it. The physics of galaxy formation is actually also much better understood than it was a while ago, but there's still a lot of work to do. And so one of the things that has changed also in the last 10 years is that people began to understand that the growth of galaxy is slightly different from what the standard hierarchical galaxy formation picture was. So the idea was that dark halos merge to make bigger and bigger galaxies, and gas falls in, and gets shock heated to the virial temperature of the halo, and then cools down into a disk. And people began to understand that actually no gas might fall in among these cold filaments. The cooling times are much shorter, and so this smooth inflow is much more important than people had originally appreciated, although there might actually have been in. So here is one of these simulations. This is Kira's law. We're one of the first that published papers on this, how the galaxies get their gas, a very nice title. So here you see, as a function of redshift, the total accretion of galaxies, the cold mode accretion and the hot mode accretion, which was this original, and then it grows by mergers, and it grows by gas plus mergers. And so what you see is that in the early universe, really this cold mode accretion of cooler gas falling in along the strings is very, very important. It dominates the growth of galaxies until maybe redshift 2 or 3. Then the hot mode accretion becomes more important, but still at redshift 0, some of that accretion is going on. And this cold mode accretion depends on halo mass. So it depends, I just showed you, depends on redshift, depends on halo mass. and it depends on local density. So what you see here is at C equals 3 and T equals 0. So let's first look at T equals 0. You see that here at the larger halo masses, this cosmological accretion has disappeared. But for the smaller galaxies, you might still see this inflow of this cold gas. And then if you go to the lowest density environments, where you see here the local galaxy density, you again see that the cosmological accretion becomes important in the very lowest density. So these are sort of roughly the predictions of the simulations. I know there's a lot of work being done, there's a lot of disagreement these days on what exactly happens. But the main picture is that at high redshift, cosmological accretion is very important. At low redshift, in the larger halos, it becomes totally unimportant, but maybe in smaller galaxies, maybe in low density environments, it is still important. And to me, when I first heard about this, I said, this is the first thing that looks like the observations that we see. So I actually like these models really well. I think it has a lot to do with what we really see. And so for me, one of the things I was thinking about is that when Christine asked me, what should I say about you? She didn't say about me. The last time I was in Heidelberg was 25 years ago. And it was a fantastic conference here on interactions and dynamics of galaxies. I don't know where it was, but I know it was. I'm not sure, maybe that was only the university. Anyway, it was the first conference where, number one, an international conference where I gave a talk, and it was about info in galaxies. That's info in galaxies. And the other thing that was really interesting, we had a big discussion where we brought up the fact that around merging galaxies, there seemed to be more gas than the gas that's in two galaxies. And so at that time, we had this tour who said, this is what all observers seem to say, already had this idea that there was more gas around galaxies than you actually see. And somehow this is being brought in, maybe by mergers. So it was fascinating. So since then I've done a ton of other things, not so much on this. But that was in Heidelberg. It was really great. So now I want to show you a few things about what observers know and people don't always talk about very much. So one is this plot that's been made by Captain Krakow, where you see on this axis the H1 mass of galaxies, and on this axis you see stellar mass. And this line is H1 equals stellar mass. And these processes are alpha galaxies. The red points are voids. I will talk later about voids. But I think one of the things that you notice is this transition. So this is now redshift 0, right? So there's this transition that galaxies smaller than a few times 10 to the 9 really have much more mass and gas than stars. It's not many people seem to realize. Well, if you go beyond this transition, galaxies have less mass and gas than stars. So that must be important for something. And then actually, the other thing I say from this talk, but this talk might show it even more clearly. So it doesn't make much sense to take the fraction of H1 gas to stellar mass. Because what you see here is, so this is now all alpha data, and that's overlap with strong data, so there are stellar masses, and that was made by Natasha Meadows. So you see here the stellar mass going from, say, 10 to the 6 to 2 times 10 to the 11. H1 mass spans in much smaller range, and that is on this side, this is totally real. So there is a sharp upper limit of total H1 mass, and actually it barely depends on stellar mass. Right? It's a few times 10 to the 11. That's it. This is the local universe. So there is no galaxies that could 10 to the 11 or 10 to the 12. They don't exist. Which is something that's interesting you probably need to think about. And the other thing you need to think about is that, so if you take a given stellar mass, there's actually a few orders of magnitude in H1 mass, and here this plot is highly biased. It doesn't have upper limits, it doesn't have low H1 masses, so actually the range is probably much larger. So you cannot have a stellar mass and predict this is what the H1 mass is. There's a huge span. Okay? So I think H1 content is, I think the most interesting thing is this upper limit and this small turnout for the lowest masses. That might tell you something about galaxy formation. Okay, that's one thing missing. Then the other thing everybody now knows is that star formation rate goes down dramatically between a redshift of 1 and 0. Right? That's observationally very well established. And there are now very interesting papers, and one is this review by Untitled that star formation might be sustained by gas accretion. So the big question is, why does the star formation go down? And so maybe the answer is in gas accretion. It might stop. And what do we know about H1 content? So little. So this is omega H1 as function of redshift. So we know really well at redshift 0, that was alpha, there's high pass, there's very good measurements. And then here there are some measurements from delta and alpha systems. They have pretty small error bars too. And here there are some measurements of stacking of H1, so optically known galaxies, and they have huge error bars. So what this suggests is, I guess, that it might increase pretty sharply between redshift 0 and 0.2, but you can't really trust these measurements very well. So what I will talk about is what I started doing is actually image directly in H1 galaxies from redshift 0 to 0.5, and so that will give a somewhat better measurement of this. But this is still another thing that's really not that well known. Okay, and then the last thing I want to show is, again, something I want to just remind you of. Before people started talking about Colloquium quantum accretion, there were actually observers, Eric Wilcox and Miller, that knew that gas was forming into galaxies. And I think this is still one of the best evidences. So this is one of these tiny galaxies, IC10 in the upper group. It has a huge extended H1 and looks like a mass. But what's most convincing that it really looks like a complicated mass, and it's not just, first of all, it doesn't look like a gravitational interaction, and the reason is that there is huge discontinuities in velocity. So I think that might actually be the best way to distinguish between interactions and info. That for interactions you should set some coherent velocity patterns, which you don't see in this galaxy. So they wrote in 1998, we see a galaxy in a local group that's still forming, still a big mass. Okay. So that's the observational point of view. Okay, so now I want to show you some observational results, and I guess many of you might know. One is the work by Catherine Krakow on void galaxies in local void. So this is all work out of redshift 0.06, so this is actually even less. So the idea here was to see how galaxies grow in local voids. It's a low density environment, it's like a low omega universe, so they should grow slowly. And so the question is that true? And is there any weird things happening with the gas? Because they're small galaxies. So for this we used, first of all, we used a very good method to actually geometrically select voids. So we used this Voronoi tessellation to describe the large-scale structure, and then we used what is called the watershed void finder, which is very good in finding the deepest underdensities in voids. And here are some examples of that. So this is STS footprint. Here is this density field that we used with this tessellation method we derived. And then here is we used the watershed void finder, which finds the deepest underdensities. And so when it's white, it's the deepest underdensity, and there was a little galaxy, and that is what it looks like. So we had a whole selection of these galaxies. Here you see the number of them. And so in total we looked at 60 voids, and here they are. And so you see that all the red points are void galaxies. So I just want to give a few highlights of this, because maybe not many of you have looked much at void galaxies. They're not often. So first of all, you see all morphologies. So you see early time, and you see late time. So most are star-forming disks or star-forming tiny disks. Tiny things. I think those are the most interesting. And actually one of the most interesting things is that there are no massive galaxies in the void. The highest stellar mass is less than 3 times 10 to the 10 solar masses. So they have only small galaxies, which is pretty interesting. The other thing is that actually, since this was a geometrically selected sample, and not a color, it has no color by it, they actually trace the whole color range. So the red points here are the void galaxies, and this is just a sloan. diagram of polar magnitude diagram of the stone survey. And so what you see is that actually it's kind of full range, but there are no bright void. They're tiny. That's one result. And so this is what I think the most interesting result. So if you look at H1 at void galaxies, you find that they are tiny, but they have in H1, that's the contours that have very large extent. And so these large extent, they're usually rotating disks, but they have very interesting weird things happening. And so one thing was this galaxy that we found quite a while ago, which is this galaxy rotates like this. The disk rotates perpendicular to it, so this is a huge polar disk. And so the question is, what made this polar disk? So in very deep UV observations, there is absolutely no stellar light there. It's only gas. The galaxy itself is flat. It doesn't have a bulge. So it doesn't seem that it has been moving. Right? So basically we think this might be, and there's more mass in gas than there is in the stars. That's the other interesting thing. So we think this might be a good example of a galaxy where gas has been retreating onto it gently. And that is how you can form this polar disk. So it's not merging really. So now you can look in a local void. I guess you all know that we live close to one of the largest voids known. And there's a tiny galaxy in there, KK246, and so can you image that too in H1. The interesting thing is, so it is just like the void galaxies that we found in the voids that we looked at for the void survey. So it has a pretty regular velocity field, except it's kinematically not aligned with the disk. And then it has here this big deviation in velocity. So we think this might be another example of gas falling in, so it disturbed the gas right at that point. Okay, and then we found some gaseous filaments in the void. So that's another thing I actually really would like to emphasize, that there are several places where if you look at one galaxy, you find a number of galaxies, and they're all embedded in one thin H1 stream. So that simulation suggests that you form filaments in void, along which you again form galaxies. The interesting thing is that the gas is that cool that you see it in H1. And so there's another example of this by Richard Wiggle. So this is, again, this is all more or less at the same velocity. It is really, really interesting. So I think we find filaments in void. So a few of the conclusions of the survey are that by looking in void, you find interesting galaxies. They're small, they're gas-rich, most of them are from stars, and the gas looks disturbed, as if gas might be falling in. Are they different from small galaxies at other places? No. But so it is basically by looking in the void, you only see things that have been growing very slowly. And you might find those things somewhere else too. And there's lots of other studies now of void galaxies, and they all find that they're very rapidly, which is interesting. Jacqueline just has a paper out in SPH that shows again that they're pretty poor, but not different from other small galaxies, which is interesting or disappointing. Okay, so there is two papers that came out that I thought were really interesting, and I just want to mention them. One is by Tim Peebles, who has been talking about the void problem for a long time. But actually, he looks at it, for one thing is there may be not enough dwarfs in the void. But the other problem he points out is that there are, if you look at the distribution of the higher mass galaxies, just in the local neighborhood, they are not quite distributed rightly. You would think that the highest mass galaxies are the highest density regions, and he points out there's actually quite a few here, here, and here. Those are very massive, but they are not in the highest density regions. Now, I think that's interesting. At the same time, another paper came out that actually pointed out, for a totally different reason, these same galaxies. And that's a paper by Tom Cormandy, who complains that all the galaxies in the local neighborhood out to 8 megaparsec, if you look at the most massive spirals, then 11 out of 20 don't have a bulge. And he includes the Milky Way. And he said, how is it that these galaxies can become so big without forming a bulge? Right? Because when you start merging to really grow, you form a bulge. Now, I think this is very interesting, not there are these big galaxies, 6946 is one, M101 is one, that are sitting out there and they cannot form the proper gold. But what is also interesting about these galaxies is that they are the best examples yet for gas info. So I think these are the galaxies that actually show that they might just be grown by gentle inflow of gas. And one is M101, that's been known forever, 1988 already, so this is the total H1. If you look at the velocity field, you see that there's a whole bunch of H1 which is really displaced from the general stream of velocities. So it's displaced by more than 150 kilometers per second. That seems, and it's just impossible to have outflow with that velocity and that amount of gas. So the usual interpretation now is this is inflow, and maybe an even better example is SG6946, which everybody at MPI labels at the center of this galaxy because it's very interesting. But in fact, it also has a very interesting outer H1 disk. And there, if you look, so this star formation is sort of here, but if you look at the outer disk and you take slices in velocity, you see that there is these big dips. And so again, one possible interpretation is that that is gas forming. So this is AGC6946, in case you didn't know it is in a void. It's really nearby, but it is in a void. And so it's one of these galaxies that might actually be grown by gentle inflow of gas. Just to think about. Okay, so now I go to the other extreme, and that is to the next part of the galaxy distribution in clusters. And again, here I want to just make the point that images can tell you a lot about what is happening in H1 images tell you a lot about the physics that is happening to the galaxies. So in clusters where galaxies fall in, they might get affected by a whole bunch of things, interactions, gravitational interactions, and reverse stripping by the hot gas. So we did this survey of 53 spirals in Virgo located in different positions with different star formation properties. The idea was to get very high quality H1 observations and then compare it with simulations to see whether we can say what happened to the galaxies. And get integral field IFU observations in parts of the strip disks to see what the stellar population are like. And so that has worked out really, really well. So this is, again, I want to just point out a few highlights. So this is total H1 images of all galaxies that we imaged. And here you see the hot gas in the Virgo cluster. All these images have been blown up by a factor of 10, the H1 images, so that you can see that. And so, of course, the first thing you see is that right in the center there are only tiny H1 disks. Further out, they are much larger. But if you look a bit more careful, okay, so these are this is D25 for these galaxies, this is the H1. So within the center, the disks are much smaller than the optical extent, which is something which you only find in the centers of clusters, and that is very likely due to reverse stripping. If you go out a bit further, you see that galaxies have H1 that's comparable to the stellar distribution, and then there are some far away that actually have small H1 disks. And that's really interesting because you can learn a lot about how that has happened. That must be an interesting thing. So here's a compilation of some of the results. So this is, here you see typical interacting galaxy, you see there actually some optical thing. And in the outer part of Virgo, which I don't want to talk about today, but you see these filaments come in the cluster and actually show there's galaxies along these filaments, and they're actually more gas-rich than field galaxies. So again, there I think these galaxies are still collecting gas into the galaxies. And so this is one example actually for a neighborhood that has way too much gas and it's very extended. So if you look further into the cluster, this galaxy has optically is more extended than the H1, so we think that's being stripped. Here's another good example for H2. The optical extends further, which you can barely see. But again, that might be a stripped galaxy. So here, unfortunately, it's way to the right here. This has an undisturbed stellar disk that extends that far, and the H1 is clearly being pushed out. And then here you see a few that have stellar disks that are much larger than the H1 disks. So they are that seems to be a clear example of ram pressure stripping. There's just no other thing. So one global effect that we saw in here was that if you look at about the virial radius of the cluster, you find that there is a whole bunch of galaxies that have these H1 tails. You see it. And if you look what direction these tails point, they'll all point away from the center of the cluster. So we think this was caused by some global mechanism, and the global mechanism is not gravity. We estimated that it can't possibly do it, but it could be reference stripping. And the reason that it could be that is because it is really the most loosely bound gas in the outer parts of the galaxies. So it's just, so at the virial radius you would say that ram pressure stripping is really taking place on a large scale. Okay, so now if you go further, there was this one galaxy, now you can see it. This is NCZ 452. And I just want to show you, this is a galaxy way, way beyond the virial radius of Virgo. But this morphology shows that it seems to be experiencing ongoing ram pressure stripping. And that's very interesting because right there, the X-ray density is not very high. It wouldn't be enough to do the stripping. And so we have additional observations that now, first of all, one of the observations we have is this integral field unit spectroscopy here, where we can look at the spectrum of the stars at the location where stripping last occurs, right? So the stripping works from the outside in. So here there must have been very strong ram pressure stripping, and this suggests that the galaxy got stripped about 120 years ago, because there's strong ball lines, right? So basically we estimate from that this happened very, very recently. Though the galaxy could not have been stripped by going through the center of the cluster, because that would take way too long. It takes more like 700 megayears or something. So this is evidence that it got stripped in the outer parts. And our interpretation is that it probably happened because hot gas is falling in, there's a subcrystal forming in, and it stirs up the gas, so ram pressure depends on V squared. So the ram pressure can easily go up by a factor 10, and that will be enough to do the stripping. Which tells you that actually the assembly of clusters might affect galaxies out of our very large distances, which is another, I think, really, really interesting thing. But so we did a lot of this IFU work on the stripped galaxies all over the cluster, and that is interesting because that gives the time scale for stripping, and it gives you some idea of the orbital histories. So these are the galaxies that were done. They were all done by QPro. So they're distributed all over the cluster. And so now we have these galaxies. We know that they've been stripped. We know when they were stripped. And now we can see what that stripping does to their evolution. So we look at the global colors of these galaxies and see where they lie on a color magnitude diagram. And that's what this shows. So this is a color magnitude diagram. This is again Sloan, and the crosses are the Viva galaxies. So what you see here is there is Viva, and the Viva galaxies are of course all disks, right? They're spirals. So they had no business being on the right sequence, but in fact they are doing it. Quite a few. There's also quite a few in the blue cloud, and then there is an unusual large number in the green valley. So that's basically what you see. Just to these galaxies, they evolve differently in the cluster, which is interesting. But now I also want to point out one thing that I find fascinating, which is that you can now look at what these galaxies at different locations look like in H1. And so you can compare the H1 extent to the optical extent. And this is what it shows. So this is where the blue cloud is supposed to be. This is where the H1 extent is equal to the optical extent. And you see that all the galaxies in the blue cloud have H1 which is larger than it. Which I'm not sure why that should be significant, but what it says is that the reservoir of H1 actually still has something to do with the star formation. Right? Because the star formation happens in a disk and there is CO in the center. But still, the blue galaxies are the galaxies that have H1 that is actually much larger than the optical. And so on the red sequence, it's exactly the opposite. All the galaxies have H1 extents that are really, really small. They still have CO in the center, and they're still forming some stars, but if you look at the global colors, they are really red. So that's basically what's happening. So removing that outer H1 is apparently still pretty important for the evolution of the galaxies. And so here you see this is basically the galaxies at three different locations. One is here, that has been very heavily stripped, and you see the spectrum it looks like a galaxy that was stripped quite a while ago, more than 400 megayears. Where here is the galaxy that I showed before, 452, which shows a spectrum that was stripped about 100 megayears ago. So now we know, at least in a cluster, how long it takes for a galaxy to evolve and cross the ring zone. It's a few hundred megayears. That's the conclusion to this. So I thought that was interesting. Okay, so these are the conclusions from looking at the cluster, that when pressure stripping definitely plays a role, although there are many other things that can play a role too. And so it can transform galaxies, at least the color evolution. I'm not too sure actually about morphology. And quality of the data, that's actually most important, is now good enough that you can really learn something about the orbital histories of these galaxies. And then a point that I just alluded to from NGC 452, there are galaxies in the outer parts of the cluster that have been stripped really recently, and that suggests that it is due to the structure of the ICM, intercluster medium, and the turbulence. That's what we think the interpretation is. So they get stripped already far out. So there's a whole thing. So actually, I think the assembly of the cluster has an impact on the evolution of the galaxies quite far away from the assembly of the cluster, which you could call pre-processing if you want. Okay, and so of course we now know that the reverse stripping is, everybody is talking about it, it's becoming more important. It might also play a big role in small galaxies falling into the neighborhoods of bigger galaxies. So that's the same structure. Okay, so now I'm going to be a bit futuristic. And so the first thing I want to talk about is this. Okay, so this picture shows you just one of these slices of the universe. You see here redshift, this goes from 0.05 to 0.25. This is slow. This is alpha. So that is alpha is this fantastic survey, this RSCBO, that this map has found H1 content in all the galaxies in this volume. But it doesn't go out very far, right? So this is all we know about it. It's really the local universe. And that's basically because of the backends of receivers, they don't go very far. Now, Westerbork got upgraded before the VLA, and so that was the first telescope, imaging telescope, that was capable of doing a large instantaneous pulse of images. That's just the electronics. And so what we did there was we said, okay, let's do a volume centered on two clusters of galaxies. So one is Abel 963, the other is Abel 2192. So that was, in one observation, a pretty deep observation, a much larger volume, with an imaging instrument. So these are the two clusters. Abel 963 was actually selected because it's a Brüter-Ullmann cluster. It's a redshift of 0.2, and it was one of the first clusters where this Brüter-Ullmann effect showed that there is actually in clusters an increase of the number of blue galaxies in centers of clusters. We actually think in this case that is still the case. There is quite a few blue galaxies in the center. Abel 2192 is much more diffuse, but we now think that's more like a forming cluster. So here is actually the total H1 ring image of Abel 963, and so here are overlays that you don't see at all. But what it shows is that, for example, this first of all, the center of the cluster, you don't see an H1 because there is no H1. So none of the galaxies in the center get detected. Even the blue galaxies don't get detected. This is very interesting. But so this is actually, these are huge H1 clouds that encompass several galaxies. So these joint H1 envelope of many galaxies. And so the total number of detections is about 160 galaxies. And with this, so here, yeah, you can't see this at all, right? There is, here, this is all in one H1 envelope. You see a whole bunch of galaxies. You have to believe me. So there's the interesting things that you can do with this. So Yara Jaffe has been working on this. And one of the things is she's been optically analyzing this, looking at spectra, velocities, positions, and star formation properties from the optical spectra. And so she found a whole bunch of substructure in AL202, and she calls this cluster information. It's just different tones falling in. So we can now relate that to the H1 properties. That's interesting too. But another thing that she did, which was really, really interesting, is she used the so-called phase space diagram, where on one axis you see R over R normalized by R200, so here is about R200, and here is the relative velocity to the mean velocity of the cluster. And so what you see here in grayscale is the galaxy density, and so what is plotted here is the galaxies, and the blue squares are the H1 detections. And so she's been comparing this to simulations of cluster formation, just dark matter simulations, and you say each dark halo gets an H1 disk, and then you can calculate at what location the H1 disk will be stripped to below the detection limit. And so there's some amazing things here. So this is the escape velocity from the cluster. So this is sort of the info region, where lots and lots of galaxies get detected. This is when the galaxies, so the galaxies will move in this plot along trajectories like that. So they get scattered and they get close to the center of the cluster, and then slowly, because of dynamical friction, they come in a virialized core. Right? And so what you see is that galaxies, where she expects them to be stripped about here, this line, and this line, and they get stripped. There's only one detection here, which is pretty cool. It's actually amazingly good. And so here in the center, there's no galaxies with H1. So now the question is, how about these blue galaxies? So here you see the same plot, but now you also see the colors, the blue and red of the galaxies, and so here you see all the detections. And you notice that here, there's actually a bunch of blue galaxies that were put to earlier galaxies that apparently already have lost their gas. So they must still take some time to turn red, but they won't be forming stars very much because the H1 is no longer there. So we catch them just at the moment that they will stop forming stars. And so here there really is no point. Another interesting thing is that there are actually a lot of red galaxies in the formula. And we think that, again, that might be pre-processing. So it could either happen before they start falling in or because of the structure of the ICM. So this turns out to be an extremely interesting way to look at the data. Okay, so now, what is happening? So since then, the last decade, as probably many of you know, the VLA got this complete overhaul. And it's now about a factor 10 more powerful in every possible measure. And so for spectral line, one of the amazing things is that you can instantaneously observe a huge velocity range. And so that is what you see here. So this is the survey that I'm currently undertaking. It's the Chile survey. So in one pointing, you probe from redshift 0 to redshift 0.5. And you image all the galaxies that are in the beam. So we have a field of about 40 by 40 Earth minutes, an angular resolution of 5 Earth seconds, and a velocity resolution of 6 kilometers per second. And we get all the galaxies. So to start that, we first did a pilot while the VLA was still being commissioned, and so that could go to 20. So this is something I think is amazing. It's called CLH, the Cosmos H1 Large Extragalactic Survey. And so what we do is we selected a field in the Cosmos field because there is a wealth of other data, so it was an obvious choice. It makes everything very, very easy. And we got actually 1,002 hours. We asked that, but it will be spread over many view arrays. So in a way, this is actually SKA-like science, right? So you can directly image H1 out of redshift. But in another way, it's a pathfinder for all the SKA pathfinders because they all want to do this. So this SDAP, Apple, Meerkat, they all want to look at redshift H1, but they aren't quite there yet. And actually, they might not be, they have different strengths. in the VLA. So this is part of the collaboration, and what I want to point out is not only that we like beer, but one of the important things is that we have collaborators from all over the world. So from all the SKA pathfinders, there are collaborators in this group. So it's USA, South Africa, Germany, Australia, Netherlands, Korea, and now Chile too. Which is very good, so we can all learn from each other. It's a great collaboration. And so the main scientific motivation, I'm sure you understand, one is to look at atrial morphology as a function of rotation in the galaxy cluster. That's what I was talking about, so now we can do this over this huge volume and see whether actually galaxies become more gas-rich at redshift of point P or 0.4, etc. So we will be able to do, so we want to see whether this accretion won't really change the redshift, but again, we can see that. So we get the content morphology in kinematics, and of course we get the H1 mass function, we get omega H1, evolution of television. We can do one of those things as this. We can look at a given type of galaxy, do stacking, and see how it evolves. But we can do more. So one is transient. So for the pilot, we actually compared it with benchmark. So we are observing every day like 6 hours, and it will be spread over 5 years. So it's a very good thing to do transits as well, and sensitivity is very, very good. We also get very deep continuum studies, and so here I want to point out something really, really interesting, which is when I was writing this proposal, Chris Hens came to me, who was a Jansky at the VLA, and he said, can I do conventional observing with your project? At that point, I don't know, I haven't done any conventional observing, but he had figured out that it was possible. So this back end of the VLA is now so powerful that not only can you get 31,000 velocity channels to do this very big probe, you still have some subbands left that are actually pretty broad. So you get incredibly sensitive continuum observations, and you get full polarization gains. So that's what Chris Hales is doing. He has this whole other team now, and it's called Chiles. Chiles produces a little bit of polarization. And so the main science drivers are, first of all, galaxy evolution. He will be able to detect like a Milky Way-like star from the galaxy out to a redshift of 3 in continuum, which is really pretty unique. He will also be able to, so his main interest is the origin of cosmic magnetism, so he can look at Faraday rotation, background sources, and actually really probe the evolution of magnetic fields of redshift. He also wants to use this as a probe for reglensing. So when you do reglensing, you don't know, you know that galaxies get deformed by the intervening mass, but you don't know whether there is any alignment in the galaxies that are actually being lensed, right? And so that might be that you start out with something that is already at 1, and it's not a lensing. But the positioning of the polarization will not be affected. So it is a way to sort of calibrate out that effect. And he calls this it's just a pathfinder for the SKA, that will do this perfectly well, but it's a fantastic project. So this is just a byproduct of this Chillers project. And so if we compare the VLA to the other SKA pathfinders, then the VLA has some amazing advantage, which is that it's up and running. The correlator is more powerful than any of the client pathfinders. The sensitivity of Meerkat is the only one that will actually be comparable to the VLA. So Meerkat will eventually be as sensitive, and the baseline distribution is very different for the different pathfinders. So actually the VLAs, you can easily use a resolution of 5 or 8 seconds. All these other pathfinders actually have most baselines at much smaller distances, so they have a good surface brightness this sensitivity, but unfortunately they are also very sensitive to RFI. And Meerkat will eventually get the same angular resolution as 5 per second, but not in the first version of that. Of course, the weakness is a really big weakness. It's a multi-user instrument, so it's not that easy to get it scheduled. And we have already had problems with that, so it will just take longer. And it has a relatively small field of view. Of course, these pathfinders are all built so that they have enormous field of view. That's the the new way of doing surveys, right? I have this very extensive thing. So, but nevertheless, we do. So, I'll show you the results of the pilot, which actually have already been published, and then I'll show you some beginnings of the real survey. So, the pilot was only 60 hours, and it was designed so that we would be able to detect the most gas-rich galaxies known locally at the redshift of 0.2, which was a known-true redshift of 0.2. So it is 32 subbands in this case, and 16,000 velocity channels. And so the detection limits at equals 0.07, which is sort of the edge of alpha. The subtimes tend to negate, so that's already pretty good. But at equals 0.2, it's 1.3 times 10 to the 10. The photon density sensitivity is, even though it's B-ray, it's 3 times 10 to the 19, which is really, really good. And so this is the resolution, of course, depends on distance. So it is 350 parsec at 60 megaparsec and 70 kiloparsec at equals 0.2, which still gives interesting information. So just to give you some idea what the VLA used to do and what it does now. So in the old days, we used 6 megahertz bandwidth, 31 velocity channels, that was sort of the channel extended mode of observing, velocity resolution of 14 kilometers per second, and a velocity coverage of 1200. So nowadays, the pilot is half the real survey, 230 megahertz, 16,000 channels, velocity resolution of 3.5, and going from 0 to about 0.2. So it's just totally revolutionary. So did it work? So first of all, so this is the pointing that we selected in the cosmos field. So this is the cosmos field. And so one of the reasons for selecting it, it is almost in the central region where most of the surveys are, but it's not completely ideal. And one of the reasons for selecting that is there is no strong continuity, which is for us important. Okay, and so this is the sensitivity. So what you see here is this is alpha. These points here is distance. This is H1 mass. So this is all the detections. This is high pass. This is the pilot, 5 sigma sensitivity. So we go much further out and are much more sensitive. And so that is the real survey. And so for the real survey, we have the same sensitivity limit as for the pilot. At the largest redshift, 0.5, we want to be able to detect the most gas-rich galaxies that we know today in the local universe. And of course, we hope that galaxies at the redshift of 0.5 are more gas-rich. So then we will detect a lot more. Okay, so this is the result of the pilot, which is really, really neat. It shows you a number of things. So this is the distribution of the spectroscopically known galaxies in this region. Red is the detected galaxies. And so here you just see one slice. So one thing we have is we have a real ball here, and actually pretty large for it. It's pretty neat. And what you see here is H1 overlays of galaxies in the different environments. So this is a galaxy in a locally really empty region, and what you see is a small galaxy with a huge H1 envelope, just like what we saw in the photo. If you go to a slightly higher density environment, you actually detect more than one galaxy in the field, and it might just be a little blue. If you go to the wall, you see something that seems to be merging, and then this is the highest redshift detection, and it looks like a mess. Right? But so basically, in this survey, the H1 morphology actually does give a lot of information. And so in the Chellis survey, the resolution will be at the largest distances about a factor 2 worse, but we still will be able to see whether gas is inside the galaxy or outside the galaxy. This tells us something about accretion. Okay, and so we use this also to stack the galaxies. So in the model we could stack it. There were about 80 galaxies, and we get a detection of 2 times 10 to the 9 solar masses, which is actually slightly lower than the average in the field. So that suggests that maybe that high density environment already has some effect. Okay, so that is, and now why is this so difficult? I just want to show you. It's called RFI, radio frequency interference, and it's all due to you guys using cell phones. Right? And all these satellites up there. So what you see here is, okay, yeah. So this is the frequency range of the pilot. This is the frequency range of the whole TELES survey, and this is just a spectrum taken on site at the VLA. And that spectrum looks the same wherever you are. You can be in Perth, you can be in the Kruger Desert in South Africa. You will always be affected by these stupid satellites. So this should be flat, and it isn't. Now, fortunately, we actually could deal with that pretty well. So this is again the result of the pilot. You see that we found over the whole frequency range almost the theoretical noise, which is amazing when you just saw that RF5 volt. But actually we dealt with it pretty well. There's a little bit left. And so now you can say, well, why is it left there? And so we looked at the synthesized beam and we found that where there is most RF5, the beam actually has become smaller. And the reason is that all the short spacings were removed because of the RFI. They had to flag this. So what that said, and that shows that much better. So this is the different frequencies. This is baseline lengths. And so what you see is that the baseline is removed at the RFI is much higher for the short spacing than the long spacing. So this is an important consideration now when you do these surveys. You're actually much better off if you have longer spacing, even though your surface brightness sensitivity is not good. But this is also demonstrated by Westerbork, which only has short spacings. And here you see, well, so the Westerbork survey was done between 2005 and 2008. And so during that time, a number of satellites came online. And so what you see is that here, the data got completely flat. So this is, I really would like to ask you not to use self-picture. So this is a picture of all the satellites. So the conclusion from the pilot is that this project really should be possible, which many people doubted. And the reason they doubted is because of the RFI. So the good thing about the VLA is that you can use the B array and that mitigates the load. The other challenge is data rate. And so with the new survey now we get 1.5 terabyte for every 6 hours of data. So if you put all this data together, you have hundreds of terabytes. This is no fun to work with. So you have to find algorithms to compress the data rate. I think that is now one of the most important things people should work on and do work on. So we had one for the pilot. We used longer average times for short spacings than long spacings. That reduced the volume by a factor of 3. And so the good news for radio astronomers that use the VLA is that they're working on an imaging program that is almost working, which will allow us to compress the data rate from 100 terabytes to about 1. And it is by putting the UV data in the gridded UV plane. So every day we can just add new UV data, grid it, and we are left with a very small database, which will be amazing. Okay, so what we do is we go from 0 to 0.5 with 31,000 channels, and that's really all you need to know. So this is the interesting plot. So we can estimate how many galaxies we should detect in this survey. And so what you see here is two totally independent estimates. So first of all, it's the cosmos field, so there is a huge number of spectroscopically known galaxies. Now there is this correlation between color and H1 mass, which is one of the few tight relations between optical and H1. And so we use that to estimate how many galaxies in this redshift range we will detect. So this is 5 sigma detection rate. These are all the galaxies that we expect to detect. So we will get 300 H1 images if things go well. Of course, you can get more. Right? This is not all the galaxies that are there by good light detection. The H1 mass might go up at higher Z, so then we will also have more H1 detection. So then we make a totally independent estimate, which is you use the H1 mass function. So let's forget about the galaxies that are there. Just say what is the typical H1 mass function integrated over this volume. How many detectors do you get? And you get actually a remarkably similar number. So we think this is pretty robust. We really expect that in 5 years from now we have H1 images for about 300 galaxies out of the redshift of 0.5. This is not that important. So now, we started observing this last year, right? We got the first 180 hours will continue in February. So this is the first time ever that you see a spectrum of 16,000 galaxies, 16,000 velocity channels over the whole redshift range. And so one of the encouraging things is that, so the pilot went about to here, and this is a really massive place, that's all of our pilot, but then actually there's a home range where it doesn't get much worse. So I think you really can go out to about 0.45 before your sensitivity will start to kill you. Now the other thing is that in the other plot I showed you, you get all these different subbands and they give gaps in the spectrum. So we now use frequency dithering, and that works actually remarkably well. So normally at the edges of the band, the noise would go up by a factor 2. If you use frequency dithering, the noise goes up by about 0.2. So that is working really well as well. So these are the different edges, so-called edges. And so finally, here's a combination of all these, of six hours data, 3 times 6 hours, showing that we actually, the noise integrates down, and it seems to be really, really good. So both the frequency dithering works and then the noise is going down. So the RFI is maybe at 0.2, it's might be worse. And if you go beyond that, it gets better again. And so if you take a low of the spectrum, you have a detection there. So things are working. That's the good news. So we hope to get lots of great science, but you have to wait about 5 years, maybe. Hopefully less. Hopefully we get it. So I just want to point out, this is really just the beginning. Meerkat is being constructed in South Africa, and ASCAP is actually already making some images, so it's very different, but it's also, it's beginning to work, and then Aperitif is an upgrade of Vesterbork where you also get this novel beams in. So there's 3 new telescopes that will get lots and lots of great survey data, and they're all coming online in the next few years. And then eventually ASCAP will be built, but that might be a little bit longer. So they have lots of high resolution Meerkat will go deeper, and Jacqueline will be able to, if it ever gets built, he'll be able to image galaxies beyond C+1, which is amazing. So the most interesting thing I saw when I went to Meerkat, that's the last slide, is the nest of social beaver birds. So if you drive along, it looks actually just like Socorro or Kulu Desert. It's just like the plains of St. Augustine, but the big difference is that occasionally there are these poles, you see this huge nest, and you say, what is that? Turns out it's these social beavers. They start by building a small nest, and then more birds come in, and they add to the nest. So if you look at it, you see hundreds of birds coming in and out of the nest. So that by itself should be a reason for you in radio astronomy. That's it.
Okay, great. Are there any questions for Jacqueline from students or postdocs? Okay, from anyone else?
A question about the filaments. Are you able to follow the H1 falling along the filament, and how far can you go away from a galaxy?
Well, so that's a big question. So
limiting factor, is it time density or is it temperature?
that is another question for forward. So the limitation for us is the primary beam response. So you see the primary beam response goes down within about 59 minutes. So you can see filaments to a certain size, but then your sensitivity goes really down. But we found other filaments that they can be hundreds of kilowatts. I think it would be very interesting to follow up, but then you need to do different things. It hasn't been done yet. I think this is definitely, they call this SBA science, but I think it could also be Aperitif science. It would actually be really good Aperitif science. Yeah. Yes?
When you refer to the gas content in galaxies, you were entirely focusing on the H1 part.
Yes.
You know, we know from, in particular, when you go to the more massive galaxies, we know where the H1 is going, right? It's going to form molecular gas, and then there's a lot of gas actually in that phase. So
I
the
think
discrepancy is not as big as you showed in the
so
very
what is the question? Or
It's more like a comment, right? When you showed how the H1 fraction is going down as a function of stellar mass, I mean, you said...
So the molecular gases, it will make a difference over factor 2.
Well, not for
Which is like, so in that fault, our galaxy, right, has about the same amount of gas in H1 as in molecules. It was way below that. It has much less than 1. So if you go to higher redshift, there seem to be galaxies that have huge amount of molecular gas, but we don't know what the H1 is. So my biased view, which is very different I think from your biased view, is that the molecular gas is just a disturbance. It goes to gas flows through a phase. So the gas falls in and at some point it becomes molecular and forms stars. And it does that at a constant rate, which for Frank, Charles, right? The star formation is just proportional to the number of clouds. So that's a constant decreasing rate. But it has to get H1 to keep forming stars. And that is actually why I pointed out this thing in Virgo, that the blue galaxies are the ones that have H1 reservoirs. There's also a paper by Sheila Kanaka, right, which shows that it is the H1 reservoir that determines how many stars have been formed in the last billion. So it's a different perspective. I know you need molecular clouds to form the stars, but to get the molecular clouds, I think you need the H1.
The opposite is not necessarily true. From them mathematical systems, you see this huge H1 reservoirs that they have got. You hardly see any ultraviolet.
Right, but I'm not saying the opposite. Right? Which is interesting. I mean, that is one of the interesting things. Small galaxies have huge H1 reservoirs, and they're not forming stars very rapidly. That's the interesting question. Why is that? Yes.
A question on your void galaxies. If you convert the magnetic half into the masses, total masses, is the ratio of the total masses to the H1 masses any different from the void clusters than the normal ones?
You mean the dynamical mass? The dynamical mass versus... No, so that is, I mean, Jacqueline has the expression that she always says that void galaxies are just like other galaxies. The only difference is that in void, you only find a small galaxy. And that's just because they're growing slowly. But if you have a small galaxy outside the void, it will be very similar. Yes.
How many usable H1 absorption spectra do you expect from chilies?
Unfortunately, almost none.
Oh.
And the reason is this field was selected to only have very weak continuum. So we will actually, we expect hundreds of continuum sources, but the limits will not be any better than from the initial. So yeah, we will definitely try. But there's other fields that will be much better for that.